And today we're going to talk a little bit about Linus Pauling and specifically his role in elucidating the structure of DNA. So Linus Pauling is a pretty famous chemist. We'll talk much more about him, but I thought I would just start with getting some conversation going. So I know maybe not everybody on the call is a chemist, but when you took your first science class or chemistry class, think back to those days in high school or college, and I'm curious, what characteristics did you think when you were entering that classroom or when you were sort of falling in love with science? What did you think made a successful scientist?
Patience.
Patience, okay. Very good.
They're smart.
Okay, they're smart. Yeah, I see in the chat being inquisitive and persistence. Absolutely. Awe. Okay, so maybe looking at the world around you with a sense of awe and wanting to understand it.
Curiosity.
Yeah, absolutely. Finding our chem teachers as inspirational. So Dr. Gunther brings up a Black woman who taught her and broke some stereotypes, absolutely. And I see skeptic in the chat too. Yeah, if they had a Nobel Prize, that made him a good chemist. I will sometimes fall into that when I'm trying to, talk to students about new reactions. It's like, well, this person got a Nobel Prize, so obviously he's important. Good. All right, and these questions about I'm not sure and science communicating, these might start to get to my second question. We have already an expert in Linus Pauling too, this vitamin C comment. The second question that I have is, if you did choose a scientific career, whether it be in medicine or really anything else in science, what characteristics do you see now in scientists that you admire? So I heard that good science communicator is something that now seems to be important. Some dedication, absolutely. Perseverance, yeah, not all of your ideas may have changed from when you first came into a classroom to sort of what you see now. Willing to be wrong. So that's perhaps another theme of my talk. Collaboration, very good, yeah. Sharing instead of competing, okay, and enjoyment. Good mentors, so bringing in others in the conversation. Knowing their limits. Following the data, okay. I love how we're coming up with sort of all these different aspects of a scientist, but all who kind of create this picture of someone who might be successful. So I'll admit that sometimes when I hear people who are coming into science or chemistry, oftentimes what I hear them say, and I didn't hear any of you say it, but they like science because there's a right answer. Has anybody ever heard that? This idea that, discussions that you can have in other courses, you don't leave feeling like you understand what the right answer is. There's all this discussion back and forth, but what's the conclusion? And in science, oftentimes you're evaluated on a test, right? So it's worth a number of points. You're right or you're wrong. You can be more wrong and lose more points, right? But there is a key, there's an answer key, something that you're supposed to get to. You have an equation, maybe it's an ice table, which might bring back some memories for some of you, right? And you have to understand how to solve these problems. I think for me, moving past that and actually acting as a scientist, it's less about knowing exactly the right answer and getting it right, and more about what's a good question. So these ideas of curiosity, right? I had to learn really a lot to understand what is a good question. But at the end of the day, for me, asking questions is really what science is about. And I tend to admire the scientists who can look at a body of literature, a field of science, and to say, like, this is an important question, and this is where I'm going to spend my time. And part of that was really inspired by someone who many of you may know, Rich Dallinger. When I first came to Wabash 10 years ago, he was a mentor of mine in the chemistry department. And he gave me this book called Ignorance, which I'm not featuring in this particular talk, but I come back to it every once in a while, from Stuart Firestein. And it's all about asking questions. It's, again, about kind of knowing what questions are good questions and how to go about them when you don't even know what the answer might be. And that kind of not being sure about what's around the corner. So there's almost an exhilaration to being a scientist. And now that I'm a little bit more advanced in my career, whereas in the beginning, I often, and I think students often, look to the teacher to tell them exactly what's right. And college, especially when I teach intermediate organic chemistry, right, is a transition between, you know, what's always the right answer to how do I deal with this set of conditions, and having more than one answer, but which one is the best one, and then trying to kind of develop into someone who can ask questions. So I thought I'd put in maybe a little bit of humor. I have a 3-year-old and she watches Sesame Street. And their theme for season 51 is one I love. It's their scientific method. The way they phrase it is, I wonder, what if, let's try. So I love this because my daughter's using it, and, you know, she's going around our yard saying, you know, I wonder what's causing that thing. What if we go get a magnifying glass and look at it? Let's try, right? So it's got this enthusiasm about it and this way of asking questions. And I see in the chat sort of the science doesn't start with, of course, right? Eureka, but maybe like, that's weird. I wonder what's going on. And I think that's really true. So with all that kind of framing in mind, I was reading this book by Sam Kean called The Disappearing Spoon. I was reading it just for fun, and it's full of stories. He's a writer for the New York Times, writes scientific topics for the public. And you know, as I was going through these chapters, some of them were really interesting to me and some of them were not so interesting to me, but they were about history and the people who did the science and how different elements in the periodic table actually affected our world, our society, our technology, but also our politics and all kinds of different things. And there is this like 3 or 4 pages in there about Linus Pauling and sort of this big mistake he made. And I thought, that is so cool. And then I went down a rabbit hole, and anybody who's been, you know, at Wabash knows what that's like, right? Coming across something that's really cool and then just diving in. So I want to give a lot of credit at the beginning to this this website, the Special Collections and Archives Research Center at Oregon State University. We'll really quickly kind of see how this is connected to Linus Pauling. But they have a ton of information and really original documents, photos, things like that that are accessible. So if you want to travel down the rabbit hole, this is a great place to go. If I had another week, I would spend the whole time on this website. It's very, very cool. So that's kind of my credit from the beginning of where I'm getting a lot of the images here. So now I want to know a little bit about you guys. We already had a vitamin C throwout, so I know somebody knows something about Linus Pauling. And I'm going to ask Steve to throw up a poll to see where you guys are at. So the question is, what do you know about Linus Pauling? You've heard of him, but not that familiar. I know a little, or I know his work really well, and you can just give this talk if I need you to.
Laura, can you see these answers coming in?
Yeah.
So will you be able to share, or will I have to share?
I think I can.
Okay, cool.
All right. So I'll give you another couple seconds here to answer. Okay, and I'll go ahead and end it. All right, so a couple of you will have to correct me if I misstep, okay, because you already know his work really well. But for the majority of you, you've either, you know, not that familiar, or you're excited to learn more, just know a little. And that's good for me to know kind of where to pitch the talk. And also I do welcome correction if you'd like to jump in. So, okay, great. Thank you for that. Okay. So let's just start at the beginning for those of you who don't know much about Linus Pauling. He's this handsome gentleman on the left, and he was born in Portland, Oregon in 1901. He went to Oregon State University, which is why they have all those records, very close connection there, and got a chemical engineering degree. Then he got his PhD from Caltech, and those years are not incorrect. So very quickly going through his education here. And he focused on X-ray diffraction of crystals, which is going to play a large part in what we're going to talk about today. He was a physical chemist and mathematical physicist, so thinking a lot about calculations and sort of the small scale end of things. His wife was really influential in his life in a lot of ways. And so one of his children, Peter, will be in this talk, but they had 4 together. He did win 2 solo Nobel Prizes. Very few individuals in history have done that. One in chemistry in 1954 and a Nobel Peace Prize in 1962. And he lived for quite a long time, died in 1994. He published really a large volume of papers and books, and many of them were scientific. And this is the slide that kind of makes me want to crawl into a hole a little bit, because if you look at his career and how quickly he progressed, as Steve mentioned, I'm 10 years in and still at the associate professor level. It took Linus Pauling about 3 years to get to full professor. So he was an incredible, brilliant man. In the first 5 years at Caltech, he published 50 papers, created a whole set of rules that are still used today for thinking about crystal structures, specifically in ionic compounds. Really prolific, really big contributions to a bunch of different fields. And he collected some of his work into a book called The Nature of the Chemical Bond. So in 1939, that book came out, and many refer to it as kind of the Bible of chemistry. It had so much information that's still relevant today. In 30 years, it was cited 16,000 times, but people still cite it in the literature from time to time these days. So what were some of these contributions? I'm going to stay away from being in chemistry teacher mode for a moment and just show them to you. So if you have some chemistry knowledge in the background, you can make a kind of association of the types of things that he contributed to. So orbital hybridization. These are images from the book that I currently teach in organic chemistry. And so these are concepts that Linus Pauling really helped to develop, but are still just fundamental to what we talk about day in and day out in our chemistry courses today. So orbitals were already known, but Linus Pauling talked about hybridization, where you might see 2 orbitals overlap and then combine. And so you might have that happen in a constructive way. So one side of the orbital gets bigger, or in a destructive way, so the other side gets smaller. This kind of mixing, this sort of place in between, was part of what Linus Pauling was really great at, thinking about these kinds of things from a quantum mechanical point of view. The nature of a chemical bond, his covalent bonds. So he was an expert in ionic bonds and ionic crystals from his PhD. And it was understood that covalent bonds were shared electrons. But he really felt that the bond was this spectrum, and that in between there was this thing called a polar covalent bond, which you may have heard of if you've ever studied chemistry, right? So it's still a covalent shared electron situation, but one atom is going to take more than the other. So again, it's not quite the extremes, but it's kind of a mix in between. And if you've ever heard of electronegativity, that's Linus Pauling. So if you look at an electronegativity table, there are numbers that can be associated with each atom and how much they want to pull those electrons, right? How their tendency to want electrons. It's measured in the Pauling scale. So Linus Pauling, contributed so much to this that while it's been slightly refined over the years, the basic concept is still his. Not just that, but my favorite R word, resonance. So you've had a class with me. This is the answer to most questions. And so the idea of something like benzene had been around for a while from Kekulé, but they thought of it kind of as switching in between two structures really fast. So an interconversion between, with these double bonds moving around the ring back and forth. Linus Pauling was comfortable in that kind of intermediate space, and he is the one who really talked about a hybrid resonance structure. So it's neither the one on the left nor the one on the right, but something that's in between, right? This hybrid structure here. And that's really hard to conceptualize as you're moving through your chemistry career as a student. It's hard to conceptualize that we can't really draw what this looks like, but it was something that really describes the phenomenon well. Okay, not only that, but in years following here in a publication in 1949, he entered not just sort of the small scale, but into the larger scale of diseases and biomolecules. So Linus Pauling was among the team that sort of first had the idea that a molecule could cause a disease. So in this case, hemoglobin, a protein, if it's different between sort of a normal patient and a sickle cell anemia patient. And we know that well these days, that proteins can cause diseases, but he was among the first to really kind of demonstrate that through some famous experiments that figure like this in his paper. So in a lot of ways, he's called the father of molecular biology because of some of this work. And he made a real name for himself in protein structure as well. So on the left here, you'll see Linus Pauling and Robert Corey. Corey is his partner in the DNA work as well. He did a lot of calculations with Linus Pauling. And on the right-hand side here, this is Herman Branson, who was a physicist. And they looked at the very well understood amino acid kind of subunit. And through Linus Pauling's understanding of resonance theory, that's this image on the bottom left, had the idea that, well, it's not really just the structure on the left, there is some double bond character there, and so everything has to be planar, and if everything's planar, then it has to be arranged in a certain way. And you can kind of see how using that idea of resonance theory and some really great images from X-ray crystallography could add together a model of what proteins might start to look like. So on the left here, you see the alpha helix, which is a secondary structure of proteins. On the right, it's a gamma helix, which is a little bit less prevalent. I'll just point out a couple things here because they relate to the DNA conversation. So if you look really closely, or if you know about proteins, the backbone, this kind of spiral, this backbone is entirely, right, formed by hydrogen bonding network of these amides. Then you have sort of R groups or side chains that stick off out into space. And so those are in this image too. It's hard to see, but these R groups are undefined and they stick off into space because the important part of the structure is the backbone, right? The thing that's twisting around and sticking together, hydrogen bonding. This is going to be important in the way that people approached DNA as well. So part of his kind of genius here again was thinking in the in-between. So a lot of scientists were trying to think of how many amino acids as an integer number might happen in a turn of the helix, and he and his colleagues went to non-integer numbers to find structures that made a lot of sense. This work was meticulously done. It had a lot of data behind it. There was an understanding of all of the amino acid sort of subunits. It was really monumental. The other sort of secondary structure of proteins that you may be familiar with are beta sheets. And in the same year, in the same journal, Linus Pauling talked about that structure as well. And again, I'll just point out that these resonance forms, so these are images from the paper itself, these resonance forms were important in informing his understanding how these planar structures come together. So we had some model building involved, but it was really based in chemical knowledge and in understanding data and calculations. All right, so this is setting the stage. Now, along the way, he and his colleagues weren't the only ones working on this, of course. There was a competition. There's always a competition in science for the next best thing. And oftentimes in competition, he was competing against this man, Sir William Lawrence Bragg. So Linus Pauling had this passion for proteins. He thought that they were the most important molecules to understand. He actually thought that they were the things that carried genes. So they were the things that gave hereditary traits. And so that was really his passion. Bragg was with him there. And Bragg had a long history as well of success, right? So in 1915, he won a Nobel Prize with his father for X-ray crystallography, again, a theme in this story. And he had a large team of people he was working with who included names that may seem familiar: James Watson, Francis Crick, and Peter Pauling, who's Linus Pauling's son. So Peter Pauling was actually kind of a person who allowed communication from both sides. So he often wrote home to his father. His father would tell him when he had ideas. He would communicate those to people in his group, like Watson and Crick, and vice versa. So he didn't necessarily pick sides, but there was open communication between scientists in this story. Again, their focus in 1951, where we'll sort of start our race for the DNA structure, was on proteins. There was some earlier data that suggested that DNA actually transferred genetic information, which we know is true, but oftentimes it was sort of ignored or not taken as seriously because the experiments were done in bacteria. And so they thought, well, that's different. That's a different system. Proteins are where it's at. So this is the image that people had to work with from DNA. Everybody had access to this, including Linus Pauling. It's published X-ray data, and I keep saying they're involved in X-ray crystallography. This is what some of the data would look like. Then this is from William Asbury. And I don't expect you to be able to read X-ray crystal data. I don't know exactly how to read it. But I do want you to just kind of look at some of these images and notice that if you're looking for, you can see that there's some dense areas here, right? And you can maybe see some of the distances between the dense areas, but these rings are kind of blurry. And so measurements taken from this kind of data are not going to be very exact. And undoubtedly, this data is imperfect. Everyone understood that, but this is what they had at the time to work from. Now, they also knew something about the structure of the nucleotide, which I've shown here. But so they understood the parts, right? There was a phosphate, there was a sugar, and there was this big bulky base. They didn't know everything about it. It wasn't as well understood as maybe the amino acid structure, but they did have these sort of pieces. Particularly the bases were not fully understood in 1951. That came a little bit later. But they knew they were big and bulky. And so in analogy to the alpha helix of protein, right? The thought was those R groups on amino acids, the side chains stick out into space because they're big and bulky and they can interact with things. Well, the bases, which are big and bulky, probably stick out into space too. And maybe that regularity of whatever structure is there in DNA comes from the phosphate and the sugar. This was not an uncommon sort of hypothesis for scientists at the time. And even the ones who we are really familiar with, Watson and Crick, who are shown here on the left, they proposed a triple helix, so 3 strands wrapping around each other with the phosphate groups on the inside. And they felt pretty sure that you couldn't have negative charges all next to each other, which I hope everyone who knows anything about electrostatics would agree that the negative charges next to each other are bad. So they said, let's just suggest there might be some small ions in there, like calcium or magnesium, that are going to stabilize those negative charges, okay? Watson and Crick were quite a team. So Watson was young. He was a postdoc, and Crick was a pretty old graduate student. They had really different personalities, but they hit it off. Their project was actually to work on proteins, not on DNA, but they both thought DNA was important. So they did that work at a lot of times in their own time. And then there was a different team of scientists, Maurice Wilkins and Rosalind Franklin, working at a different institution. And Wilkins is kind of the tie between Watson and Crick and Rosalind Franklin. So you may not know Wilkins and Franklin as well, unless you've taken a class with me, in which case you should remember Rosalind Franklin, because she's one of my personal heroes. But she went and looked at Watson and Crick's original triple helix and said, there's no way. She did X-ray crystallography with DNA, and she found that DNA absorbed water somewhere around 10 times more than what they proposed. She said it's thirsty, right? So there's no way that with that much water, that would start to displace the ions, and then you would have the whole thing blow apart. So she told them in not very gentle terms, right, that this was silly, that's not going to be correct, it doesn't match her data. So they sort of put that off to the side, went back to their proteins, and kind of went on with things, but still were thinking about the problem. Then Rosalind Franklin took this gorgeous data. So remember the data that I showed you earlier where everything was blurry? This is photo 51, and this changed everything. So Rosalind Franklin took this image with Raymond Gosling, who worked with her in the lab. And the difference here is that they allowed water to interact with DNA. So it was wet. It was able to soak up that water, which allowed it to be extended. And then it was in its pure form. It wasn't a mixed form, which it turns out led to that blurry data I showed you earlier from Asbury. And, you know, as I drew your attention the first time to some of the more dense areas, you can see that you can actually calculate the distance here between dense areas. You could actually measure the angle between these sort of X's that occurs, right? The distances are much more clear. And all of those pieces of information from this image tell you about DNA. It tells you about how tight the turn is, how far the gap is in that double helix structure that we come to know as DNA. All of that information comes from this data, and it's just beautiful. So we talk about that kind of awe that scientists have. This is how I feel about this data, right? It's art to me. So Linus Pauling was actually in England when this data was sort of being talked about and passed around, mostly without Rosalind Franklin's permission. He didn't see it. So he took this trip to England, and he was really focused on proteins. He still thought proteins were the key. He met with people about proteins, and he did not see the data when he went to England in 1952. There's some sort of legend to this story that there were politics involved, because he did have his passport rejected after being accused of being a communist. But he was able to get a temporary passport and still make a trip in May of 1952. So I think it's probably more likely that he just didn't focus on DNA while he was there, than he was held back from being able to see the image by politics. Okay, so he missed this. He didn't have this data, but he was really good at solving problems. And in 1952, Alfred Hershey and Martha Chase sort of proved in their experiments, if prove is a word you can use in science, which is debatable, that DNA is the genetic material. Okay, so they had radio-labeled DNA. They were able to show that that is what a virus uses to replicate, and so that carries genetic information. And then everyone turned their attention to DNA. And what we'll see is that this is a pivotal time, and Linus Pauling, who has been really good at thinking about structures, doing these calculations, is going to turn his attention to DNA. And at the end of 1952, December 31st, he and his partner, Robert Corey, submitted their proposal for the nucleic acids. I'll show you some of the images from this original paper, which was published in, I think, February of 1953. And you'll see that some of what I've already talked about becomes an issue in this particular structure. So let me decode this a little bit. These are original images. So, or paper images from the original paper. So each of these squares is a phosphate group, and the circle in the middle is the phosphine, the dotted circle, and then the solid circles are oxygens. So they imagined that you would have three, this triple helix that was often proposed, that you would have three of them, and these phosphate groups would really meet in the middle. They knew that you couldn't have negative charges right next to each other, so they felt that the oxygens of the phosphate groups must be protonated. They must still have a hydrogen on them, so they don't have a negative charge. There's very little that would suggest that this is possible. So when reading about this, right, the idea is that I've discovered is that Pauling would sort of change the model a little, take it to Corey, and he would say, well, these calculations don't make sense. And he would change it just a little and then try to kind of force it into something that might allow that proton to stay on. They knew that was an issue for them, right? So here's another image where those phosphate groups are down the center. So this is looking from the side, and you can see the sugar group, and then here's this big base that's out on the side. And the thought was, you know, if this carries the genetic information, then it's available, right? Just like those side chains in the alpha helix, they're out there, they're ready to be read and transmitted. But the center still had issues, and they seem to know it from the language in the paper when they proposed it. They called it a promising structure, a very tight one, saying it accounts moderately well for the data, that Astbury data that was out there. Reasonable satisfactory agreement, which is very tempered language, right? And it's probably capable of further refinement. So they know they're just getting an idea out there, right? They're just making a proposal, but they feel confident enough that they've published it as, you know, sort of a first step. And Pauling really talked about this as something that that he felt was true, and that the details would be worked out later. Here it is, kind of looking from the top, so you can see it from different angles with all those big bases, the purine and the pyrimidine bases, sort of splayed out and not having any kind of steric clashes in the middle. All right, so this is out there in 1953 in February. And in the background, of course, Watson and Crick are still working on their data. So by Pauling's own theories, right, there are issues. The phosphate groups should ionize. But also there's this data that he sort of didn't account for in his model from Erwin Chargaff. So Chargaff did have conversations with Pauling, as the story is told. He was a strong personality and maybe not one that you'd love to have long conversations with. And so perhaps that might be part of why Pauling didn't count this as sort of central to his model. But this is really important, turns out to be really important to our understanding of DNA. He found that there were equal amounts of adenine and thymine, so this bigger ring paired with a smaller ring, and then equal amounts of guanine and cytosine, so a bigger ring paired with a smaller ring. Many of you will realize that these are the pairs that you always find. So if those bases are sticking out into space, there's no reason to have equal amounts of them, right? If you flip it into the model that we know today, this makes a lot of sense. And so here's an image of one of the original models from Watson and Crick. And in April of 1953, just 2 months after Pauling published his theory, his hypothesis, Watson and Crick published theirs. They didn't do it alone by any means. They were really model builders, and Jerry Donahue, who got an acknowledgement in this original paper, was one of the ones that helped them to clarify what was going on in those bases, because there were some, as I mentioned, some like inconsistencies with how they understood the bases. He helped them to see, if we're getting technical, that it was the enol form instead of the keto form, and that kind of made everything click into space. Rosalind Franklin's data was certainly critical. Shargoff's results made a lot of sense with this. And so these paired bases are at the center of the double helix, and the phosphate groups with negative charges are on the outside, soaking up that water. This was a Nature paper, and there were 3 papers that were published back to back to back. This paper was actually only 825 words. It was very brief. It put forward the model. It was easy to read and understand. And then the 2 papers after that in sequence were Maurice Wilkins, and Rosalind Franklin, with a lot of the data, much more complex and more difficult to kind of crack, to understand what's going on, but really that strength of evidence for this model. So in April, before it was officially published, Linus Pauling learned of this structure. And he planned a trip in the first week of April to go to Cambridge to actually see what was going on. And essentially, he knew right away, once he saw Rosalind Franklin's data, that they were correct. So this is an original letter from Linus to his wife about, while he was on the trip, he talks all about, oh, I had dinner with this person and we're doing these things. And at the very end, he says, I've seen the King's College nucleic acid pictures. That's the photo 51, and talked with Watson and Crick. And I think that our structure is probably wrong and theirs is right. So within a very short period of time, privately, Linus Pauling has sort of admitted that his hypothesis was incorrect. He did this in private conversations with Watson and Crick too. James Watson would recall that he gave his opinion gracefully that they had the answer. I can't imagine how disappointing that would be for Linus Pauling, right? To get to that point, to believe in your model, to put it out there, and then to basically see someone else's model and data and say, nope, that's right, I was wrong. But he not only admitted that privately, he also very publicly, very quickly threw his support behind Watson and Crick's model. So I include this quote from a conference in the same month of April among, of course, scientific colleagues to say, although it's only 2 months since Professor Corey and I published our proposed structure for the nucleic acid, I think we must admit it's probably wrong. Although some refinement might be made, I feel it's very likely that the Watson and Crick structure is essentially correct. So I am just really impressed, I think, with the response that Linus Pauling had privately and publicly to this whole situation, right? And sort of the mistakes that were made along the way. And I think he needs to get credit for the way that he handles that situation, just as much as the work that he put in a lot of ways. He did actually go on to even help that model. So he pointed out some mistakes. You can see from these images from that conference I mentioned in April of 1953, he was sort of obsessed with these bases and how they might fit together. So these are his notes. And he did find some corrections to help. Linus Pauling would say that throughout the years, he would talk about things that sort of led to this very public mistake. And he said, well, I didn't have good x-ray photos to go off of, which is true. He did not see Rosalind Franklin's data. He also didn't ask for it, but he didn't have that data to look at. He blamed the way that he read the DNA density, and he was very much focused on the triple helix. He felt that that was critical to include, and in fact, it was a double helix. And he talked about how he didn't understand the DNA subunits and those bases as well as he did for the amino acids. So while his work in proteins and alpha helices was really measured, it had a lot of evidence behind it. The theory was well understood before that structure was published. It was quite the opposite for DNA. This wasn't his primary focus. He didn't have great data. He didn't really understand the pieces as well. And so the question becomes then, was he just in a rush to get an idea out there? Was he proud enough to think that, he understood the structure, how to propose a structure, right? And so then he kind of just put that out there too fast. And it might be a little bit of both. So I think that's definitely something to consider. And when you hear about interviews, really for the rest of Linus Pauling's life, he's asked about this very frequently. And he always has different responses, and sometimes his wife actually gets impatient with him publicly about it too. So again, a rabbit hole I won't go too far down. He did not suffer for very long, because in the next year, in 1954, he got his Nobel Prize in chemistry for his work on the nature of the chemical bond. He went on again to win a Nobel Peace Prize in 1962. So these same sort of outspoken political tendencies that were very much influenced by his wife led him to speak publicly against nuclear armament. And so the Nobel Committee recognized him in sort of a retrospective award. In 1963, they gave him the 1962 Nobel Peace Prize for his work in sort of publicly speaking out against nuclear warfare. It's also not the only mistake he's ever made. And so this is the vitamin C controversy that I mentioned earlier. So there are some doctors on the call, and you are much more experienced in medicine than I am. But in 1968, Linus Pauling published in Science, a major journal, an article named Orthomolecular Psychiatry. And so the idea behind this, as I understand it, is that giving really high doses of natural compounds like vitamins can be a treatment, he felt, for mentally ill patients, including things like schizophrenia. He felt very strongly that it was a good treatment for cancer. He argued for intravenous, high concentration vitamin C treatment for cancer, and felt that the clinical trials that were done were not thorough enough. He felt that vitamin C could cure heart disease and, of course, the cold and flu. So I will tell you, I still take vitamin C when I feel a cold coming on. I won't ask you to raise your hand, but I'm guessing I'm not alone. And so it's kind of funny to realize that, okay, my doctor here is telling me that's not a good idea. It's kind of funny that this influence, right, has traveled down into some of our behaviors, even currently. And there's no scientific evidence that vitamin C has an effect on any of these things. So I think that's another fascinating tale, but not the DNA structure that I'm here to talk about. So now I want to hear from you guys, and you can unmute. Again, you can use the chat, and I'll kind of try to navigate. What do you feel like can be taken away from the story of Linus Pauling specifically in this kind of race to understand DNA?
Hi, this is Bill Cadis. Could you hear me?
Yeah.
Yeah, hi. I'm a PhD in organic chemist and acolyte of the just passed David Phillips, a fellow NU student. I got my PhD at Northwestern after Wabash. The comment I want to make, my perspective on Pauling is mainly from the inorganic bonding and the quantum, hybridization side. But when we get in the 60s, 70s, and 80s, clearly he was trying to fit experimental results to his familiar, comfortable models of chemical bonding. So he became a captive of his paradigm. So to invoke Thomas Kuhn and his, the paradigm shift in scientific revolutions, new ideas, Kuhn's idea was that new ideas come in science when you have the paradigm shift, the revolutionary way of thinking, and then your opponents die out over time. But I think to a certain degree, Pauling was still publishing using his bond models long after they had kind of dropped by the wayside. It was like Einstein and the unified field theory. Physical theorists felt sorry for Einstein that he had fallen off the path of discovery. I think it was similar with Pauling. He was trapped by his prior thinking to some degree.
Thanks for that, Bill. And I felt that too when I kind of looked into the parallels between alpha helices for proteins and DNA. This is, of course, how those things must connect, right? But it isn't. You have to think differently. You have to have a new perspective. And I see that too from Dr. Roberts, who says, you know, a little liberal arts might be helpful too, right? And maybe a bit less siloed.
I hadn't occurred to me before, but Pauling, what had occurred to me, Pauling is an enormous model maker. He has a book where before computers had diagrams, he had an artist draw diagrams of complex structures and so on. And he would have accepted the Watson-Crick thing because it was a model. And he thought in terms of mental models, of three-dimensional models. And that's why it was so easy to convince him.
That's a really good point. So he could see it, right? And it was a language that he spoke. He could see the beauty of the model.
Yes, yes.
Yeah, that's a great point. I see a quote here in the chat too, but I'm not going to read the whole thing. So, yeah.
Mr. Talbot, I see raising his hand.
Well, considering the fact that I lived through all of this, and when I was in law school, my roommate, my fraternity brother from Wabash, Tony Caney, was a microbiologist at Illinois. So I always was heard the edges of these stories. And my reaction to your presentation, Dr. Wysocki, is that we've been shown how people of great intellect, but also great character, can say, I'm wrong, you're right, I will help you be better. And I think that is the whole sense of what science is about, isn't it?
Yeah.
You have leaders who've got to lead and help, and they make mistakes, and they just move on and do the job right.
I love that. And especially because I think we're living sometimes in a time when if you make a mistake, it follows you everywhere you go, right? But mistakes are an important part of discovery. And recognizing them and building from them are critical, absolutely.
Sorry. I think the model actually also is what convinced Watson and Crick that they were right. Crick had deciphered the structure from the X-ray, and they thought they had it, but they didn't really realize it all went together until they built the models and saw that it actually physically fit at the scale they built it at.
Yeah. Great point. And I think that's part of why Jerry Donahue got an acknowledgement, because that last piece really clicked it all into place for them, how the bases fit together.
One of the really interesting things is Franklin's role and what Pauling might have thought if he'd been able to see those X-rays.
Yeah, absolutely. And Rosalind Franklin was not interested in collaborating. She wanted to she was very focused on her experiments, and she wanted to get all of that experimental data done before building a model. So I think that that's an interesting kind of piece too, that the data clarified it to a point where the model made sense, and they went hand in hand, really. To see them both together was critical in understanding.
Hi, this is Bill again. Laura, if you can talk a bit more about Rosalind Franklin and her subsequent place in medical history, because being a bunch of guys, she was not actively talked about in the Wabash of the early 70s in biochemistry. So who is Rosalind Franklin and why is she important? And what do people think of her today in 2 minutes or less?
Yeah, absolutely. Well, I could give an hour, but I'll try to hold to 2 minutes. So she's one of my personal heroes for a lot of reasons. One, because she was so focused on the data, as I've been kind of talking about here. She was not well respected by Watson and Crick in her lifetime. And it wasn't until I think it was the 80s when Watson actually admitted that her photo was part of the key in understanding DNA. So she did not get a lot of credit. She passed away at 37 from cancer. It's unknown whether that cancer was because it was hereditary or because of her experiments. The safety back then wasn't really what it is now. She was unmarried, so her death certificate says she was a spinster. And I think within the last, I would say 30 years, she's getting a lot more attention as someone who is critical in this process. And part of the reason why she didn't win the Nobel Prize is because she was already dead. So Wilkins, you can't win a Nobel Prize if you're dead, right? So Wilkins sort of took her place in some ways. And there's a big question about whether she would have been elevated to the level of Nobel Prize worthy if she were still alive.
I think she was actually quite close with Crick and his wife. I think she, in fact, lived with them as she was dying of cancer, as I recall.
Okay.
Yeah.
Well, if you'll let me, in the last couple minutes that I have you here, I want to tell you one of my sort of takeaways from this and how I bring it to the classroom. So I'm going to skip this question about failure because I think that we've talked a little bit about it. When I look at students that I have in my classroom today, I see a lot of what I also identify with as imposter syndrome. This idea that everybody else has it together and I have no idea what's going on, and there's anxiety to that, there's panic to that, there's questioning about why they are where they are. And there's no real mystery to that, right? We live in a world of social media, and when all you see are people's successes, right? For me, it's my colleagues publishing grants that they won and papers that they published and promotions and awards, and you start to feel like what you're doing isn't quite enough. For students, it might be, you know, another 4.0 semester, I got into my first choice med school, you know, all the graduating early, whatever it is. They may see grades like I got in college, failing my first few quizzes and midterm in organic chemistry, which is my specialty now. And they might look at those grades and feel like this is not the place for them. And so what I take from this is that it's important to share stories of failure. It's important to share what you learn from that failure. And I am upfront with my students. I mean, this is being recorded and posted, so I am laying it all out there, right? That I struggled with organic chemistry in the beginning, that I understand what it's like to not succeed from the get-go, that I can hopefully work with them to learn from their failure and truly really discover if this is one of their passions and where they want to be. So this allows me to talk a little bit about science identity, which is where I want to leave this, because I think in more recent years, it's really been understood that science identity is important for student success. STEM retention, going toward their kind of final destination. The questions of, do I see myself as a scientist? Do my family and friends see me as a scientist? If the answer is yes, I see myself as a scientist, then when failure comes around, you can still identify as a scientist and work with that. But if you start to question whether that failure means that I don't belong, that this isn't for me, then you start to make other choices. And that's when we lose students from our STEM classes. So oftentimes science identity is really driven by a sense of community and affiliation. This is easy for some Wabash students, and for others it's not. So if you look around the classroom and you think everyone else belongs here and I don't know what's going on, then you might not feel that affiliation or that community with your peers. It's built by having consistent extrinsic and intrinsic things. So I feel like I'm smart and I get good grades. That's a positive thing, right? This fits my identity. But if I feel like I have an interest in science and I'm not getting good grades, then this starts to weaken and become kind of an issue. And also just a match between like what I'm learning and what I'll do, right? So school science and real science. So is what I'm doing here, is what I'm studying here reflective or going to be important in my future career? And I think that I can bring this into the classroom by talking a little bit about like normalizing failure. Linus Pauling, a brilliant man, made a mistake, right? And, you know, Laura Wysocki, the person that you're here learning organic chemistry from, failed her first organic chemistry exam in glorious fashion, right? And that's okay. And if you hit hard times too, that doesn't mean that you don't belong. It just means that you might have to try some new things as you study. So this type of thing really informs how I come to my classroom, how I think about my students, how I think about their experience, how I think about how to communicate to them when all they see are sort of the scientific greats of the world, that they were real people too. And I think that that can help with community. It can help with retention. It can help with relationships, and it can help with persistence in STEM. So, you know, these are some students that I've had in the lab. These are the photos we post. They are amazing science communicators. They win awards. They do great things. And I will tell you that not every moment in their career is bright and shining. Some of it is hard. And that's why these stories, to me as an educator, are important to bring to the classroom.
Dr. Wysocki, I have 8 o'clock,
There we go.
8:01. So are there any parting thoughts, Dr. Wysocki, from your end before we close her up?
I think that was my parting thought. Thank you
That was
for
it.
giving me that.
Okay, fantastic. Hey, thank you everybody for joining.